Good evening, everyone. My name is Zahari Dichev, and today we're going to talk about some techniques for allocation-free programming in Scala. And I'm not going to bother you with sort of introducing myself. I think Ivan already did enough, or talking about my background. We're just going to jump straight into the presentation. Something interesting to mention is that last year, I think I gave a presentation on Scala Days about performance in general. And at that point, I focused on a few different areas. And I mentioned that each one of these areas deserves its own talk. Some of them even deserve a book. So this time I picked one particular area and decided to do a presentation on it. So when we talk about object instantiation and using the heap on Scala and the JVM in general, there are a few things that are important to keep in mind. First of all, it's important to keep in mind that actual object instantiation costs time itself. It creates a lot more work for the garbage collector, and which can actually introduce systemic pauses in your application. And this is not good for performance because it introduces non-determinism. And non-determinism is really one of the most evil enemies of performance because you don't really want to be fast sometimes. What you want in a performant application is to be able to put concrete runtime guarantees on your system. So because of that, a lot of systems implement entirely GC-free data structures that live pretty much off heap. And this is fairly hard to get right, especially when you have to deal with problems like concurrency and all of that. There are also some commercial solutions that provide post-free GC implementations like the Zolzing. And as of recently, there is even a no-op GC collector implementation for JDK called the Epsilon collector, which, as a matter of fact, is quite useful if you, for example, are running really short-lived jobs and you don't want to burden your workload with the overhead of GC. Or if you're testing certain, if you want to validate certain assumptions about your system and you want to abstract yourself away from the cost of GC. On top of that, there are plenty of products that actively employ patterns to decrease allocation. So Akka, for example, in its core tries to keep allocations to a minimum. And if you go and look into the implementations, for example, for the stream interpreter and all these internal parts of this library, you'll quickly see that these guys are trying really hard to kind of keep allocations to its minimum. Native 4, for example, uses a quite interesting data structure called byte buffs, which is an off-heap reference counted data structure that almost brings you back in the days of manually allocating and deallocating memory because you have to retain it and free it when you're done and all that. Another product borrowed by my colleague Matthias Donis is well ahead of its competitors with respect to performance because, and mainly because of that, it tries to keep allocations to a minimum. And of course, there's a whole class of systems like proprietary trading engines and analytics frameworks that really actively rely on not allocating or allocating as little as possible in order to be able to uphold real-time guarantees. And thankfully, there are some pretty fundamental features in the JVM and Scala itself that you can resort to or keep in mind if allocation pressure and GC pressure are problems. So for example, things like value classes, specialized generics and specialized data structures, mindful use of certain APIs, and name-based extractors are some of these things. And of course, if you want to go a lot further, you can resort to things like of heap data structures that are available out there as library implementations. But one thing to also keep in mind when we are talking about all of this is that a lot of people actually pay quite a bit of attention to the overheads that garbage collection provides. And the truth is that it's not only GC that is the problem. Actual allocation costs time. And there is quite a bit of machinery in the JVM that kind of deals with that, right? So, and tries to make it more efficient. So what are some of the costs that you're paying when you're initializing objects on the JVM? Well, first of all, if you think about it, there are kind of three main components to creating an object on the heap, right? You have the allocation, which is literally dealing with the claiming the memory and figuring out what part of the process space to get for the data of this instance. And then you have system initialization that pretty much provides, it takes care of fulfilling the guarantees that are provided by the runtime. And then you have the user initialization that's running all of your user code, such as constructors and static initializers and whatnot. And in order to kind of minimize that, there's quite a lot of things that have been engineered into the JVM. So there are various GC implementations suitable for different workloads, and there are numerous options for configuring the behavior of your allocator and the behavior of your GC. And of course, there are various internal implementations that aim to make allocation more efficient. For example, one such thing is TLAPS, right? And TLAPS stands for Thread Local Allocation Buffers, which is a pretty sophisticated machinery for preemptive thread local allocation. And it deals with the problem of minimizing the synchronization costs effectively when multiple threads try to allocate memory at the same time, and allows for each thread to preemptively allocate a block of memory that's going to be used for all the objects that are placed on the heap. And it uses quite sophisticated heuristics to determine the block size at runtime based on the allocation pressure and other runtime characteristics of both your code and the JVM. Just to kind of show you what sort of an effect that might have on performance, we can run a very simple experiment, right? So this piece of code pretty much loops a bunch of times and allocates an array and tries to fill it with a bunch of objects. And if you run that and you use the epsilon collector, which effectively ensures that you're not experiencing any kind of GC burden, and we can run that code with TLAPS off and on. And if you do that for kind of a range of different number of objects, and you benchmark that, you quickly see that there is a significant performance difference between the case when you're running with TLAP enabled and without TLAPs, right? And this just tells you how much of a machinery there is to sort of make allocation more efficient. And the interesting part is that, the takeaways of this is that, as a matter of fact, allocation itself costs time, and there is a lot of code that is running behind the scenes that tries to make this performance burden kind of go away to a certain degree. But if you think about it, running this machinery also consumes CPU cycles. So really employing techniques to decrease your allocations can have very significant impact on your performance, especially if that's happening on like really hot paths in your code. So what can we do about all of this? So let's look at a few simple examples of how you can kind of decrease allocations. So first of all, let me just have some water. So first of all, let's look at the extractor object. And extractor objects are, all of you probably know that, but they're a great tool in Scala, right? It's an object with an unapply method which takes an instance of a class and tries to give back its components for some definition of this action. And it's very useful in pattern matching and partial functions, etc. So it's overall a great tool for achieving brevity and conciseness in your code. And what can you do with extractors? Well, a very silly example would be to extract black rooks out of a chessboard. And I don't actually play chess, but I just have a very hard time coming up with examples. So it's like, yeah, I grab to what I thought about. So if we have this code, what can we do with it? What do we want to do with it? We simply want to go through a board of rooks, right, of arbitrary size, and match on all rooks that are black and give back their coordinates. So writing an extractor that does that is, might look like this, right? So we have an unapply method, takes an instance of a rook, and if the rook is black, it's going to give you a sum of a tuple with the coordinates. Otherwise, it's going to be none if the extraction is not successful. And if you actually use any kind of bytecode analyzer to look at what's happening under the hood, you end up staring at this, most likely. And this is a pretty generic piece of code, a bytecode, right? And this is for the successful extraction, for when the rook is indeed black. So, but if you focus a bit more, you see that, you know, apart from the tuple, the specialized tuple of RT2, there is also an instance of sum being instantiated, right? So, of course, that ends up on the heap, and it's yet another allocation that you need to make. And if that's on a hot path, it certainly will have some kind of performance implications. So what can you do about that? Well, thankfully, back in the day, in Scala 2.11, name-based extractors were introduced. And this is a pretty cool feature because it allows you to, you're not obliged anymore to return an option from your extractions, right? So the only thing that you need to return is an instance of a type that defines the methods is empty and get. And if effectively, if your extraction is successful, that's determined whether by the isEmpty method, and of course you can use get to obtain the extracted object. So if you want to rewrite your extractor to actually use name-based extractors, that might very well look like this. So you have an internal representation called an extractor that effectively uses no as a guardian value, right? And it defines isEmpty and get. And if the rook is black, it's going to give you, we're going to get an extractor with the coordinates. And if it's not, we're going to get a no. So, well, we're going to get an extractor containing no. So if you take a look at this piece of bytecode, it's going to look like this, right? Sort of like this. But the interesting part about it is that it's not the colors. It's the fact that looking closely, you can't really find a instance of sum being instantiated anymore. The only thing you find is the specialized tuple of RT2. But you know, you might kind of wonder, and that's a valid question to ask, well, does this actually make much of a difference? In a lot of cases, probably no. But if you really are running on a hot path and that's something you're doing a lot, and this is not such a hard to imagine scenario, it makes quite a bit of difference. And as a matter of fact, I benchmarked this particular operation for various sizes of boards. And you can quickly see that it's very easy to spot that the default implementation where we are instantiating the option takes quite a bit more time to run. And interestingly enough, if you want to get even more stats about this whole thing, you can take a look at other statistics to kind of print your application stop time and kind of get all the GC statistics. So apart from that, you can also take a snapshot of the heap at any point and look at what's happening there. And you quickly see that in the default case, there is quite a bit of some objects being instantiated in addition to the rook objects. So this kind of tells you that, again, it's a validation that with name-based extractors, you don't really need to instantiate these some objects. Another thing that is quite interesting to look at is specialized generics. And as a matter of fact, if you are coming from a Java background, it's probably very, very possible that you have encountered at some point in your career an interview question that deals with boxing in out-boxing. It's like the run-of-the-mill thing for interviewing questions for Java developers. So really, out-boxing is an automatic conversion done by the compiler that it makes to convert a primitive value to its corresponding wrapper. So for example, if you have an int, it can get converted to java.lang.integer, which is the wrapper living on the heap, right? And Scala primitives are expressed as any vowels. And whenever they are used in generics, however, because of the way type erasure works, they are wrapped. So for example, an int used in a generic object, it will get wrapped into a java.lang.integer, which is yet another allocation. And of course, in certain scenarios, that might pose quite significant burden on your performance. So again, if we go back to our rook example, but now we have it a bit more generic. So, and let's imagine we want to go through, again, a virtual chessboard, and that's the only chessboard I've ever seen, a virtual one. So, but our chessboard now, much like Hilbert's Infinite Hotel, that has half-sized rooms, has half-sized coordinates. So you want to express the coordinates of a rook as a double, so you can have rooks that are staying at 2.5 and 3.5 and whatever. So, and if we have a piece of code that pretty much goes through this kind of board and generates rooks like that, it's very interesting to look at the bytecode that this rook creation produces, right? So if you kind of isolate the instantiation of the rook and you sort of look at the bytecode that gets spit out, you'll actually quickly see something like this. And this is, again, fairly generic, but if you zoom in a bit, you see the calls to box to double. So effectively, your primitive doubles are now getting boxed to their equivalent wrapper, right? And of course, this is not all that desirable. If you're doing that a lot, then you end up with a lot of short-lived objects, or long-lived, doesn't matter. It's just a lot of allocations. And what are some ways to actually avoid that? Well, if you think about it, you can resort to specialization. And of course, you can have only double rook class, right? But then you need to have an int rook class and a short rook class and a Boolean rook class, although I don't really know how that would look like. But nevertheless, this is not very good for your code base, right? It kind of bloats it. It introduces quite a lot of repetition, so overall it's just not great. Thankfully, there's the specialized annotation that you can use on generic types, which kind of is a hint to the compiler to do this for you, effectively. Generate separate specialized classes. Of course, this decreases your boilerplate, but on the other hand, what happens is that you might, if you overuse that, you might end up in a situation where quite a lot of bytecode is getting generated and the compilation is a lot slower. And this is effectively the reason why, or one of the reasons why specialization is used quite cautiously in the standard library. So if you look, for example, at tuples, they are specialized, I think, up to only part RET3, because obviously, if you specialize for more than RET3, you end up with like an explosion of variants of what kind of types you can have there. So if we have to rewrite our generic class to be specialized, it would sort of look like this, right? So we will specialize it for double, and then if you kind of look at the bytecode again of instantiation of a rook, you quickly see that now there is not really any kind of trace of boxing these doubles. So the only thing that you're seeing is the instantiation of this specialized class now, which has the $MCD, $SP, which stands for a specialized class for doubles. And if you look again at, if you compare the performance of the two variants, you again see that the specialized version is a lot faster compared to the default where you have the boxing occurring. And again, if you kind of do a heap dump at some point, you'll be able to see that there is, again, in the default implementation, you have all these doubles getting allocated, while in the specialized, they really aren't. So this is some of the things that you can use in order to decrease allocation in your code. But also, it's very important to kind of know what's happening under the hood when you're using certain APIs, right? And that's actually something that was part of a presentation on Scala UA that Alexander Nemec did that kind of got me interested into looking a bit more closely into that. And probably all of you know that, but like I generally am not a Scala expert, so this was kind of a surprise for me that it happens. So consider the SIG type, right? And this is a very useful abstraction for library developers because you as a library developer, you can define your methods or objects to receive a SIG, and you can pass a lot of things in there. And these SIGs, they always have defined order of elements, provide very convenient apply methods for indexing, have subtraits for that are index SIG and linear SIG that provide you with different characteristics around the runtime behavior of these objects. The interesting part, however, is that sometimes you might be very well tempted when you need to pass a SIG to do something like this, right? And it's like I was really surprised what's actually happened here, right? So I'm sure all of you know that under the hood it's a list that's getting constructed, right? But if you kind of take a step back and look what's happening, well, how is that actually happening, you realize that there is something like this, right? So an array is created with these elements, it's wrapped in an int array, and then the sig.apply method is called. And if you look at the sig.apply method, it kind of looks like this. So does a bit of checks, constructs a new builder, then kind of appends these elements to the builder, and then the list is constructed. And this new builder is really a list buffer, and that's a mutable data structure. And like focusing a bit more on the important part here, you kind of start to wonder, well, why is all of the indirection, right? And is there a better way to do that? And all of these things, again, they're allocations, right? So looking at the bytecode, you can see that there is that you're wrapping in an int array. There is this list buffer created, So I decided to kind of take a bit of a deeper look into all that and kind of see what the impact is on the performance if you're using this particular technique of instantiating a list. So imagine that you have this event, right, that has some ID and a SIG that has some other event IDs, right, that are its dependencies. And we simply want to generate a number of events, right? And we benchmark that operation for 250,000, 500,000, 1 million, and 3 million events. And so our code looks a bit like this, quite simple, right? So here we are creating a sequence that's passed to the event. And is there a better way to do it? Yeah, in fact, because this is really a list that's getting created here. What we can do instead is we can directly use the diff syntax, the cons. And what's that going to do is going to call the method on list, and that pretty much gives you a new collection. So the interesting bit is, again, how much of a difference that makes, right? I mean, these list buffers getting allocated and all of that, does that make quite a bit of difference on performance? And indeed, it does. So if you benchmark and you look at these results, you'll quickly see that when you're using scala-italy, you're significantly slower compared to just constructing the list directly. So it's very interesting to look at these kind of results, at least for me, because I didn't really know how this works under the hood, and now I understand that there is quite a lot of luggage that you need to carry just to create this list with the sig.apply method. And again, looking at the heap stats, you'll see that we have wrapped arrays of long and list buffers getting generated when you are using the apply method. So all of this is very interesting, and it deals with things that you can do in your code in order to minimize allocations, right, and thereby gain a bit of performance where needed. Another interesting thing that is used quite heavily, especially in certain industries, is completely bypassing the heap itself, right? So if you think about it, there are alternative allocation strategies, right? So you can completely bypass the heavy machinery of heap allocation and maintaining all of that data there. So, and that can allow you to maintain pretty huge heaps and incur effectively zero GC cost. And of course, as a result of that, you improve the performance characteristics of your code, but you might also get yourself into quite a bit of trouble. So going back to our events example, imagine that this time we have this event that has ID of long and a payload that's byte array. And we know a few interesting things about these events that make creating the example a lot simpler. So first of all, what we want to do is that we want to process each incoming event in some kind of a event processor logic. And we want to record its ID and store it in an ID to an event cache, right? And we know for a fact that each IDs are unique and consecutive long figures. And we also know that, surprisingly, our payload is always 64 bytes. that's not 64 bytes max, it's always 64 bytes. So a naive implementation, which is really not all that naive of such an event processor, might look something like this, right? So we have a mutable map that's going to be our cache, and we get a stream of events, and for each event we are effectively recording the last ID, and we put the cache, we put the event into the cache. So of course, if you do that long enough, you end up with a few interesting things. So there's going to be increased use of the heap if you're kind of sticking to these events for a while. And of course, there's going to be increased allocation rate for auxiliary data structures that are, map nodes and all of that, that's the internal state of the map. And as a result of that, you have increased GC activity and probably at some point unpredictable performance due to non-deterministic pauses and whatnot. So what can you do about that, right? I mean, I referred earlier to Netty using off-heap byte buffs, and they kind of made the decision in version 4 to switch to that, I think, because they realized that this is kind of one of the easy for them ways to uphold the real-time guarantees that they're trying to uphold. So what you can do is resort to using the unsafe method, the unsafe. And the JVM effectively provides a backdoor allowing you to perform a number of low-level operations for manipulating memory, interacting with threads. And it's, in fact, widely used in packages such as Java concurrent collections and util concurrent for like implementing locks and that kind of stuff, as well as in Java and I/O. And of course, this API is quite dangerous because you kind of are dealing with direct memory, and you can very well crash your JVM, which is not desirable. However, the important part about it is that you can, if used correctly, it can actually bring you pretty unparalleled performance, especially when you want to have things like especially when you start implementing things like lock-free data structures that are living entirely off heap. And there are a lot of products that actually have this functionality and are delivering it to you as libraries. So how do you get a hold of this unsafe? Well, you can import the MISC unsafe, and through some reflection, grab an instance of this, right? It's not really meant for using it by the general public, so that's why they kind of made it a bit hard to get a hold of that. And what this provides you is a few interesting things. So there's some useful methods here. You can allocate a chunk of memory, right? That's direct, and it lives off heap. And you can write longs to it, you can read longs, and all sorts of figures of different width into that block of memory that you've allocated. There are also a number of additional methods for thread synchronization and atomic operations on that memory. So it allows you to really implement very scalable lock-free data structures that live entirely off heap and just maintain caches of enormous size without incurring the cost of the garbage collection. So if we go back to our little example, it's with events, you might kind of wonder, well, how is that even useful? Well, if you think about it, this event that we're looking at, it's actually a bunch of bytes, right? So it has an ID, which is 8 bytes, and it has a payload that is 64 bytes. So if we have a block of memory and we want to write a bunch of events there, and we have this memory looking like that, I'm sure that's exactly how it looks. What you can do is that at address 0, you can write the long, you can increment your write pointer and write all the bytes, right? And then if you if you effectively want to write another event, you can just do it the next available slot. And of course, this is a very simplified example, but this can be modified to deal with objects of arbitrary size. So if we have to kind of rewrite our event cache to take advantage of that, what can you do? How can you do that? Well, you can have something like this, right? So it's an event cache of a fixed size. We get the unsafe, and we have a few variables that are helping us with the whole sizing, you know. And we know for a fact that the size of an event is the size of a long plus the size of a byte, which is a byte, of course, times the payload size, which is always 64. And what we do is that we allocate memory that is predefined. So, and we get back a pointer that we can use to write stuff. And if we want to store an event in the cache, what we can do is that we get the event and we get the right pointer. We pretty much get this right pointer at the exact place where the event should reside based on its ID. And we write a long. And then we slide the pointer by 8 bytes in order to get to the point where we should be writing the payload of the event. And we can just iterate through the array. So yeah, we can just iterate through the array, and then we can write byte by byte. And obtaining an event that's been stored in the cache is quite simple as well. It's kind of the reverse operation, right? We get the ID, we slide the read pointer to the exact location where we know our event starts, and we read the ID of the event, and then so we read along, and then we read byte by byte the payload, and then we can construct the event. So if you think about it, like again, does this make a difference? Well, yeah, indeed, it's quite it's a lot more efficient. So if you compare the execution times of this whole operation for a number of events, you quickly see that the off-heap version is significantly faster, takes quite a bit less time. And this gets even more pronounced when you're dealing with a large number of events that need to be sticking around on the heap for quite some time. And again, looking at the heap stats, you can see that in the default implementation based on a mutable map, you have all the events being in the map as well as the default entry, which is kind of a helper data structure of the map itself. So the interesting thing about unsafe is that there are actually plenty of products out there that are making use of unsafe. So for example, Chronicle Software, which is a stack of products aimed at the financial services domain, so things like high frequency trading and stock exchanges and whatnot. They use that software quite a bit. You have the Disruptor, which is quite a high performance inter-thread message fabric that I think Martin Thompson was one of the drivers behind this library, and it's at the heart of the LMAX exchange, which I think to this day is one of the fastest financial instruments exchange out there. And of course you have Neti, which are using put off heap buffers, again relying on unsafe, in order to try to uphold the real-time guarantees that they need to. And of course you have various other data structures and tools, both in the Java and Scala ecosystems, that deal with concurrency and IPC and need to be really, really fast. So you have a lot of these products making use of that kind of off-heap stuff and sort of off-heap magic. But again, this can lead to quite a bit of problems if you try to roll your own, because it's really hard to get right, and most of the time it's always better to rely on third-party things that are extensively tested. So what are some of the takeaways that we can leave with? Well, first of all, you probably all know that automatic memory management is a great feature that prevents us from shooting ourselves in the foot or in the face in some more extreme circumstances. And it's really great. I mean, like compared to writing C codes where you need to take care of all of that yourself, it's just a blessing. However, a lot of times it might very well hinder your performance significantly, especially when you're on a really hot path. So it's kind of interesting to think about this, and it's important to keep it in mind when you're designing for performance and when you want to engineer systems that exhibit certain characteristics. And the good news is that the JVM and Scala in general provide us with plenty of patterns that allow us to minimize all of this overhead, or at least part of it. And the good news is, again, there is a gamut of ready-made solutions that actually give us this functionality, such as Chronicle and all of these things that I mentioned. You can go and use an off-heap threads safe map, for example, an implementation of that in order to kind of minimize your allocations and the objects that are sticking around on the heap. So, and of course, as a last takeaway is a lot of these things, they really they require quite a bit of effort, right? So before you delve into optimizing these things to the extreme, it's always really important to measure things a few times to determine where the right spots for optimizations are. And all of that being said, I forgot to have a thank you slide, but thank you all for bearing with me, and I hope I see you next year.
Okay. We have time for a few questions.
Hi, thanks for a great talk. Actually, to my taste, the topics like this are underrepresented on Scala conferences. So it was like a breath of fresh air for me.
I'm glad.
Okay, so the question is about the future for the unsafe API. As far as I know, starting from Java 9, maybe the Java maintainers, they try to expose as much as possible of unsafe APIs, var handles, and well, as far as I know, var handles are first of this kind, but could you rely on availability of unsafe allocation in the future versions of Java, like 5 years from now?
Yeah, I think that's been there's been quite a bit of discussion around that, and obviously different opinions, but like I personally think that you probably will be able to rely on them, because, I mean, think about it, like a lot of, like there is no unsafe tomorrow, half of Wall Street goes down, right? So I think that's probably there'll be some kind of a change that sort of makes it a bit more approachable and everything. But I don't think it might change the way we use it, but I think it will probably be there because it's just not a lot of people see that in their everyday life as developers, but under the hood, a lot of tools rely on that, so I just don't see it going away. What do you think?
Well, I think everybody who moved to Java 9, Java 11, they started to see warnings on the JVM start about the complaining that unsafe is instantiated. You see it every time, so people start noticing that it's used.
Yeah, well, it will be interesting to see what kind of an alternative there will be. Maybe.
Yes, thank you very much.
Thanks.
Next one.
Hi. Do you see any future in using other techniques to improve heap allocation, like index types or things that Rust is doing, or other languages, or what do you see in that regard?
Well, I think there's some work on Scala, as far as I take it, with opaque types and all that. So this is coming. With respect to other languages, I mean, Rust is not necessarily. I'd say that it's mindful of allocations, of course, but like its main idea of the Rust compiler is not really to prevent allocations or to just minimize them to a minimum. It's more about making it safe without the overheads of GC. So, like, I think that this trend that Rust started of moving this memory management, of course, in a much more primitive version of it, from the runtime to the compiler, is something that we're probably going to see more of happening. But again, I'm not a prophet, so it's I really don't know. But I guess that's just my opinion. Of course, Rust is a very different language aimed at a very, very different audience of people, and it's that's why the approaches it uses are quite different.
Yeah. Thanks.
In future, probably we'll use Grail VM to replace the standard JVM. Mainly for this reason, unsafe was removed in Java 11. And generally, all these kinds of optimization probably will fail when we try to convert the Java native code in a VM, LLVM approach. So generally, we need to look for other kinds of optimization inside the global JVM ecosystem.
Well,
what do you think about mainly Grail VM if you test it or use it, for example?
Yeah, I'm not particularly very. I've used Grail VM for other things, or just trying to compile for like binary images, the native image stuff, and I think it's great technology, and yeah, probably that will. But it still provides quite a bit of limitations as to kind of reflection and all that, as far as I take it. I'm not really familiar with the inner workings of it. I don't know whether that will be the answer to kind of removing unsafe, and again, I really don't know. Don't really have a very strong opinion on that.
No one else? Okay, thank you again, Zahari.
Thank you.
So.